Hello, I'm gonna show you a technique called mathematical induction on an arithmetic sequence. Well, actually on the series of an arithmetic sequence. So let's say we have an arithmetic sequence given by n is a0 plus n times q. And we want to find a formula for a series of this sequence. What is a series? Series is sum of the terms of the sequence. It doesn't have to be all the terms, it can be just a subset of terms. For instance, a series of one term would just be equal to a0, right? Because that's just the first term. A series of 2 would be a0 plus a1, okay? So if we, in our arithmetic sequence, if we had a0 would be equal, let's say 3, and the q would be equal to 2, then a1 would be 3 plus n is what? N is 1, so 1 times 2. So a1 would be 3 plus 2 is 5. Okay, so series 2 for our example sequence would be 3 plus 5, which would be 8. Okay, what if we want to get a series of 20 terms or 200 terms? That'd be pretty lengthy to do it this way. Let's say that someone comes in and gives us a formula to universally calculate the series. And here it goes. So the formula would be n plus 1 times 2a0 plus n times q divided by 2 for as n that starts where n starts from 0, as n where we go up to n, k starts in at 0. So let's say that someone comes in and says, this formula is a formula you can use for your sequence and it'll always get you the series back. Now, how do we verify that's true and that this person isn't lying to us? Well, easily, not very easily, but we can use something called mathematical induction to verify that this indeed is true. And it has several steps. So the first step is find base case or prove the formula for base case. Second step would be assume the formula works for k. And 3, prove for k plus 1. Okay. So the base case basically would be would be the first term because it's easiest. In theory, it could be any term. We don't have to do the first term as the base case, but it's the easiest because we know that if we start from 0, so the series with n set to 0 would be n plus 1 times 2a0 plus n times q over 2, and now we can plug it in, so 0 plus 1 times 2a0 plus 0 times q over 2. Okay, 0 plus 1 is 1 times 2a0 over 2 plus 0 times q is 0, which all gives us just 2a0 over 2, which cancels out, the 2's cancel out, and we get back the a0. So we have now proven that the base case works with this formula, okay? Because it says that, because we said that we start from 0, k from k0 being 0, so we plugged in 0 as our base case, and we got back a2. And we already said in the beginning that the series or the summation of our sequence having only one element is gonna just have the starting element, right? So the S0 or like S of one element of the first element would always be 1, right? So now we can move to the second step, and that says that we assume that the formula would work for k or n. Sometimes it doesn't matter which variable we use, and we prove it for k plus 1. Now what does that mean? It means that, let's say we want to prove it for let's use the letter n actually, since we use n everywhere here, and n and n plus 1. Okay. So what would the summation be for s of n plus 1? What would it be? I'm pretty sure it would be Sn plus a n plus 1, right? So the sum of the n plus 1 terms would be equal to sum of n terms, and then we would just add the n plus 1 term on top of it, right? Because if n plus 1 could be 1, right? Could be 1, which is S0 we calculated before, it's A0, and S1 would be 0 plus A1, right? So that'll be the result, right? So here we'll just, instead of using Sn, we would plug in the formula that was given to us. We would plug in the green formula, and instead of a n plus 1, we would plug in our term formula for calculating a single term. Let's highlight this one with red. Okay. So the formula for an is a0 plus n times q. All right. So Sn plus 1 would be Sn. Sn is n plus 1 times 2a0 plus nq over 2 plus a0 plus n times q. N times q. But wait a second, it's not going to be n times q, right? Because we need n plus 1 element, as you can see here. We need n plus 1, we don't need n. So this would be n plus 1, right? So let me just erase it to make it very clear. So a0 plus n plus 1 times q. Now that's better. Okay, so how do we solve it? We need to simplify this formula, and hopefully we will get an output that looks like a plausible formula for as n plus 1. All right, but let me get to that step by step. So how do we work on this? So I can put everything under this umbrella because it's the same thing, because n plus 1 over 1, right, times 2a0 plus nq is the same as simply putting it all together. So we can just do that. N plus 1 times 2a0 plus nq over 2 plus, and what do we do with this? In order to add or subtract, I'm sure you know that we can just multiply it by the denominator, and that way we can express it using the same denominator. So we would just multiply by 2, so a0 plus n plus 1 times q, right, over 2. As you can see that if in theory, if I wanted to cancel out the 2's, that's an operation I could always do, and I would get the initial formula back. But I don't want to do that now, so let me put it back. So it's very clear, okay. And let's just factor everything out and see how we can rearrange this thing. So first, n times 2a0 is 2a0n plus nq plus 2a0 plus nq. I can use all. I can just put everything in the common denominator now. Plus, so what do we have here? Let's start easy. So let's just do these two expressions first. This is all one expression. All right. So it's gonna be plus 2a0 plus 2q times n plus 1, right? So we can go a little bit further, and we can go ahead and do 2a0n plus, just repeat everything, and q plus 2a0 plus nq. Oops, I think I made a mistake there. Yes. guess, up here. So 2a and q, and the other term would be n squared q. So n squared q plus 2a0 plus n q. That makes sense. All right. Plus 2a0 plus, and now factor out these guys. So it's going to be 2nq plus 2q, right? And it's all going to be over 2. All right, let's see what we can do here. So we have similar terms, 2a0n, 2a0, and 2a0. So we can factor them out as 2a0 times, what do we have left? N plus 1 plus 1, right? Close it. Let's do another one. It's gonna be this guy and this guy. So we would say and q let's see, plus and q times n plus 1, right? And we can keep going. So what do we do about these two terms? Could say plus 2q times n plus 2, right? I'm seeing that I made another mistake. No, I didn't. And q, that was 2a0 plus squared q plus 2a0 plus, okay. All right, so we can go and keep things moving. So what we can do now is we can go further. I still see these terms here. Let's use another color. These two that we could probably improve. So let's get to it. 2a0 times n plus 2. We just merge this together. Let's say plus, and now we can say just q times n plus 1 times 2, no, plus 2 that doesn't seem like it's gonna lead anywhere. This doesn't look so exciting. This doesn't look so good. So let's start over, go back a little bit, and there is a ton ton of terms like this, sometimes it just doesn't work out the way we want it, which is fine. Just do it over. Can just change the way I work on this. Okay, so which is 2a0 times n plus 2 plus, let's just write it out first, q plus nq plus 2nq plus 2q, right? What would be nice is that if we could get this term everywhere, if we could factor it out into the same term, right? So let's try something else. What if we work with these terms? What if we factor this term with this one, and then this term with this one? Then it's always gonna give us n plus 2, right? So let's get to it. Let's see. 2a0 times n plus 2, just repeating what we already have here, plus, and I would say nq times, it's gonna be n plus 2. That's the red ones. This is the red. This is the red product. Plus q times n plus 2, right? This is the yellow product here, coming from this guy and this guy here. Similarly, these two guys, right? And now we have something awesome here. If you noticed, we have n plus 2 everywhere, which is great, because now we can factor everything. So let's do it. 2a0 plus nq plus q, right? Times n plus 2, because it's all the same. It's all the same. All right? Over 2. And now this is starting to look good. Now we can further simplify the inner expression. You can probably already spot it right here. Okay. So 2a0 plus q times n plus 1 times n plus 2 over 2. Okay, and this is going to be our final product of s n plus 1. Now let me explain it to you, what this means. Let me write the original formula here to the right. So original formula that we were proving was Sn, and it was equal to n plus 1 times 2a0 plus n times q, right, over 2. All right, and what we got here is, in the green, we calculated the formula for n plus 1, and I can do a little bit of rearranging here, just moving this term in front and changing the order right here in the original formula. N times Q is the same as Q times N. Everyone knows that. So if we just rearrange the S n plus 1, we get n plus 2 times 2a0 plus q times n plus 1 over 2, right? Now, do those look similar or do those look similar? Let me highlight the n plus 1s everywhere. Well, this is kind of highlightable. You can see it's n plus 1. So the only difference here, if I try to like map it together, is that the first term is n plus 1, and this is for Sn, right? So you would say n plus 1. And for n plus 1, our term says n plus 2, or you could write it as n plus 1 plus 1, right? And inside here, we are multiplying by n plus 1 instead of n, right? And just this correlation that this formula for n plus 1 that we were able to simplify it in a way that it works, that it would translate correctly to n plus 1, is the proof that we need for and that's the core of the mathematical induction. So we basically assume that it works for n, it works for Sn, and we try to add our our formula for the next term, and we see if we can come through with it, if we can simplify it in a way that it makes sense, that it would, that those two would connect and work together. And if it works out, then then it's valid. And that's pretty much it. Thank you.